This is lesson 5.1 part 2. What we're going to do now is we're going to leave our y is equal to x squared plotted here, but we're going to erase the 3x squared and 6x squared and plot the 0.3x squared and 0.6x squared and see what the effect is of an a less than 1 on the yx squared is equal to x squared function. So let's just erase these ones here first. You could have drawn them all on the same grid. I'm just making some room because it's not as neat in the video if I don't. Okay, and now we're going to go and choose a color for our y is equal to 0.3x squared. So let's make that one maybe go with the green over here. So I'm gonna have to estimate a bit. You'll have to do a better job than I am, just because we have some decimal values here, and it's difficult to do with just a mouse. So let's take a look here. If we have y is equal to -3, then at 0.3x squared, that's 2.7. So here's 2, 3.5 is here, so just about over here. Maybe even a little lower, but that's okay for now. We're going to get the idea. When y is equal to -2, oh, sorry, I was -3, so -3. Let me erase that, I've miscounted there. So when y is equal to -3, we have 2.7, just about here. When y is equal to -2, we have 1.2, so just about here. And when y is equal to -1, we have 0.3. So 0.5 is here, so a little bit lower, just about here. Our y-intercept is 0, 0, so that's the same spot here. Then 1, we have 0.3, so just about here. Then for 2, we have 1.2, so about here. And for 3, we have 2.7, so just about here. Maybe a little lower, but again, that will do the trick. And now we can connect these dots and extend if we need to. And you might already be seeing a pattern. When a is less than 1, compare the graph to when a is equal to 1. If you look, it looks like our parabola is getting wider, like it's not stretched from the vertex like the other ones were, but instead compressed, pushed down and made wider. So if you start off with that stretched elastic and you push it down, you compress it, it becomes wider at the base from the point that you're holding it, from the vertex. Let's just draw the other one in to see if that's actually the case. So we're going to make 0.6 next. So let's just label this as y is equal to 0.3 x squared. And now we'll do y is equal to 0.6 x squared. Let's choose another color here. Let's go with this over here. So when we have -3, we have 5.4. So -3, 5.4. So just below the 5.5 mark here. When we have -2, we have 2.4. So just below the 2.5 mark over here. When we have -1, we have 0.6. So just above here. We have 0, 0 over here. Then 0.6 over here. Then at 2, we have 2.4, so about over here. And at 3, we have 5.4, so about over here. Then we can connect our dots. We can extend there. We can label our graph there, y is equal to 0.6 x squared. So what you'll notice is that the smaller this a value becomes, the more compressed our parabola becomes. So we had y times 0 So y is equal to x squared, then we had 0.6x squared, so notice the parabola is wider now, more compressed from the vertex, at the vertex. And then we had 0.3x squared, so an even smaller a value here, and it's even more compressed at the vertex and even wider. And really that's because it's rising more slowly, right? So if you look over here, when you have 0.3x squared at 1, we have 0.3, whereas 0.6x squared you have 0.6, and whereas just x squared you have 1. So for every unit, you're going up a lot faster when your a is equal to 1 or larger than 1 than you would be going up if you had an a that's smaller than 1. So when a is smaller than 1, we know that the parabola seems to be wider at the vertex. And so we're going to go and make those conclusions now on the next page, and then see a different type of transformation that we can apply to the a value, and see how that will affect our parabola of y is equal to x squared. But I hope that you can see that all we did here was take that y is equal to x squared and apply a transformation to it, which means we change the a value to make it larger than 1 or less than 1, still keeping it positive. And we saw that if it's larger than 1, we have an extension. We make the parabola narrower from the vertex. And we also see if we have a value less than 1, but still positive, we have a parabola that is going to be wider and more compressed. Notice that we've had a positive a all along, so for each of these functions here, the parabola is opening from the top. So that's no different than what we saw in the previous unit. So let's go and fill in our conclusions. So how are the graphs of y is equal to 3x squared and 6x squared related to the graph of yx squared? Well, we know that these graphs here, y is equal to 3x squared and y is equal to 6x squared, they have a greater y value. So the y values are greater for every unit of x, for sure. So for every unit of x, the y value is greater. We also know that the rise is faster for those two graphs, and it's narrowed from the vertex. So again, almost like it's being stretched. Whereas if we had 0.3x squared and 0.6x squared, well, the y values are smaller. The y values increase at a lower rate. And we also know that we are wider at the vertex. And that's because these are cases of a being less than 1 and a being more than 1 over here. So if we look at question number 4 here, how would the graphs of the following equations relate to yx squared? Well, if you were to plot yx squared and compare it to 5x squared, we'd look over here, our a is 5. So that means our a is larger than 1. So we know that this graph here is going to be narrower at the vertex than y is equal to x squared. And we also know that the y value is increasing faster. Y value increases, that means increases 5 times faster specifically. So for a unit of 1, let's say you had y is equal to x squared, y would be 1. If x was 1, y would be 1. But if you have 5x squared, if x is 1, y is 5. So they actually increase 5 times faster. Whereas if you look over here, y is equal to 0.2x squared, well, we know it's going to be wider at the vertex because our a is less than 1. Wider at vertex. And what's basically happening is the y values are increasing more slowly. So y values increase at a rate of 0.2 compared to the y is equal to x squared. So for y is equal to x squared, if x is 1, y is 1. But for y is equal to 0.2x squared, if x is 1, y is 0.2. So it's going up a lot more slowly when we have an a is less than 1. And again, the smaller that a value, the more slowly you're rising, the more wide you are. The larger the a value, the faster you're rising, the more narrow you are, the more stretched out that parabola is from the vertex. So what we've seen here is a transformation where we have positive a's, but we increase the a to be more than 1 or decrease the a to be less than 1. We saw a narrowing or a widening depending on if you had a more than 1 or less than 1. You should know those trends and how the graphs compare, just like we did in questions 1, 2, 3, and 4. And now you have some reasonable idea of what the graph should look like. I'd recommend that you go and use the Desmos calculator. I put a link on your Google Classroom. You can use that calculator in order to plot the graphs, just to do a quick check of your work to make sure that you are on the right track when it comes to graphing. And also, now we're going to go and attempt a different type of transformation, still modifying our a value, but this time we're going to have some negatives in the a value. So the role of a when it is negative. So role of a when it is negative. We have a similar type of table here we're going to fill out. Again, I'm going to walk you through how to do the basic idea behind the table, and then I'll fill it out faster, but you should pause the video and check to make sure you're on the right track. Then afterwards we'll go plot these graphs and come up with some conclusions about what effect the negative a value has. So same idea here, we have y is equal to x squared. We've already done that, so I'm just going to fill it out quickly. You're using the same x values, 9, 4, 1, 0, 1, 4, 9. Now our a over here, so this is our a is 1, our a is negative 1 over here. So when our a is negative 1, we have y is equal to, let's say x is negative 3, we have negative brackets negative 3 squared, which is going to be negative, so negative 3 squared is 9, so positive 9 there, but negative times positive 9 is negative 9, so negative 9 over here. And as you can see, we're just doing the negative of what our initial y is equal to x squared was. So here we'll have negative 4, here we'll have negative 1, here we'll have 0, then here we'll have negative 1, negative 4, and negative 9. And then likewise, we can try over here. We have our a value is negative 3. So we can go try to find the x values for, the y values for when x is equal to negative 3, negative 2, negative 1, 0, 1, 2, 3. So I'll do an example with you here. So y is equal to negative 3 times, let's put our negative 3 in there, and then square it, which is equal to negative 3 times, negative 3 squared is 9, which is negative 27. So you'll notice that we are doing not just 3 times the x squared, but also negative 3 times the x squared this time. So we're doing 3 times 9 and then times negative 1. So negative 27 over here. 3 times 4, 12, and then times negative 1, negative 12. And then 3 times 1 times negative 1, negative 3. 0. And then back to negative 3, negative 12, and negative 27. In the next video, we're going to complete this table and start graphing our functions to see how a negative a affects our y is equal to x squared.